Okay, last one. So now that you've found the calibration factor for your calorimeter, how many kilojoules or joules for every degree that it goes up, then you do your reaction with a certain mass of food in it. So you completely combust the mass of food and get the energy out of it, and then work out the temperature rise for your food, and then you can work out how many kilojoules your food released. You know how many kilojoules it was for a certain mass, so you can work out how many kilojoules per gram. So if we do an example, we've got this much of a cheese snack and it's been completely combusted in a bomb calorimeter. The calibration factor was this. During the combustion of the snack, the temperature of the water rose by that amount. So you've calibrated your calorimeter, and you know that for every 1 degree you need that many kilojoules, and when you've done your food, you've got 5 times that amount. So calculate the energy content in kilojoules per gram. So we have a calibration factor. So the amount of energy is your calibration factor, your kilojoules per degree, 1 degree, and you've done your food and it's gone up 5.8, so it's 5.8 times that amount. So your cheese snack made that many kilojoules. We want to turn that many kilojoules into the number of kilojoules for every gram of food. We've got that many kilojoules for 1.6 grams. So if we divide this by this, we'll get how many kilojoules for 1 gram. So the cheese snacks makes 22.2 kilojoules for every gram of cheese snack. Same idea with pizza. This is a different calorimeter, so it's got a different calibration factor. We do the reaction for your pizza, complete combustion, and you find that it goes up that much. So you've rearranged your calibration factor equation to get this equation to work out the amount of energy for a particular food. So you can find your pizza has that much energy and you burnt 7 grams of it, so that's how many kilojoules for every gram. So if the food is a pure molecule, then you can find the energy content per mole as opposed to the energy content per gram, because this is a mixture. So we've got pure glucose, and you can work out the kilojoules per mole or the enthalpy of combustion. So same idea. It's got the water rose, so these questions could have the initial and final temperature here. And you would have to work out the change. In this case, we want to know how many kilojoules per mole, so we're turning our mass of food into moles, and then we're working out how many kilojoules per mole. So if you divide any number by a number on the bottom, you'll get how many kilojoules per 1. If you were asked to write it as an enthalpy change, then remember that if you ever write change in H, you need to write that it's exothermic, so you're releasing heat, kilojoules per mole, and put your units on. So oleic acid was completely burnt. Calculate the enthalpy change. So this will be the same steps as the previous one. And you work out that this is the amount of energy per mole, per 1 mole of oleic acid, which would be what is written in the data booklet. So if it's written in the data booklet, then it's kilojoules per 1 mole. But if we could work out, write a complete combustion reaction, so we know we get 11,000 kilojoules for every mole. But if we did a thermochemical equation for the complete combustion of oleic acid, we need to be able to find the formula for oleic acid. And that's oleic acid is a fatty acid. So look up your data booklet and find that you'll get this. To do combustion reactions, it's easier to write the molecular formulas, how many carbons, hydrogens and oxygens. So when we're doing complete combustion, oxygen making carbon dioxide and water, we need to balance the carbons first, then the hydrogens. So you would need 18 carbons, and each water molecule's got 2 hydrogens, so you need half this. And then if we work out the amount of oxygens, you can find that we've got 2 lots of 18 and 17, so we've got 53. You need to take the oxygen away from the fuel first. So if we took 2 oxygens away, we'd get 51, which we can't divide. So anytime that you've got an even numbered carbon, you generally double the reaction. So we're doing each of these twice, so we've got twice the amount of carbons and hydrogens, so therefore twice the amount of oxygen. If we took 2 lots of 2 away, so 4 oxygens for our fuel, then we've got 102 left, which we're dividing between 2 oxygen in a molecule, so we've got 51 oxygen molecules. Alright, so if you do the change in H just for how many kilojoules for every 1 mole, then if we were doing the complete combustion reaction, we've got 2 moles, so you'd need to double this. I think that is it. Yes.